Okay, thank you, and thank you, Tawfiq, for once more giving me this opportunity to talk at your meeting. So I will talk about a generalization of the absolute order on the symmetric group and of the lattice of non-crossing partitions. I'm going to start with sort of a review of the properties of the usual absolute order and lattice of non-crossing partitions. This is going to involve a lot of poset combinatorics and some symmetric function theory. If you're not familiar with these areas, you're not going to really be able to follow the details of my talk, but you can pick up some vibes of what the subject is about. So first let me review the definition of the absolute order on the symmetric group Sn. So kappa W will be the number of cycles of a permutation W in the symmetric group Sn. So here's an example. In one line form, the permutation is 4, 2, 5, 1, 3. In a disjoint cycle notation, it's this, 1, 4, 2, 3, 5, so it has 3 cycles. And we'll define a partial ordering on the symmetric group as follows. If U and V are permutations, we'll say, actually this should be, we'll define that U is covered by V. If there is a transposition ij such that V is ij times U and the number of cycles decreases when we multiply by ij, this would mean that I and j are in different cycles of U. Multiplying by ij merges these two cycles in some way. So this will define the cover relations of the absolute order on the symmetric group, which I denote by abs Sn. Here is the absolute order on the symmetric group S3. Every time we go up, we're multiplying by some transposition and we're reducing the number of cycles. Because down here we have 3 cycles, 2 cycles, and finally 1 cycle. So the maximal elements are the single cycles. There's n-1 factorial of them. Here are some properties of the absolute order. It's a graded poset of rank n-1. Every maximal chain has n-1 element, has n elements. The elements of rank n were going to be the permutations with n-k cycles. So this sub k denotes elements of rank k in absolute order. So permutations with n-k cycles. Of course, the number of such permutations is the signless Stirling number of the first kind, C of n-k. So the number of maximal elements, as I said before, is n-1 factorial permutations with 1 cycle. The identity element is the unique minimal element of the absolute order. The rank generating function of the absolute order, this is the polynomial such that the coefficient of q to the k is the number of elements of rank k. The well-known generating function for Stirling numbers of the first kind. A nice product. 1 plus q, 1 plus 2q, up to 1 plus n-1q. The Hasse diagram of the absolute order, that is just considered as a graph. So the vertices are the elements of the symmetric group, and there's an edge between them if they differ by a transposition, if they define a cover relation in the absolute order. It's just the Cayley graph of the symmetric group with respect to the set of all transpositions. Cayley graphs in general are directed graphs, but since our generators, the transpositions are involutions, we place a double edge from U to V and V to U by a single edge UV. Since it's a Cayley graph, the Hasse diagram is vertex transitive. Moreover, since the set of generators is a conjugacy class, it follows from representation theory of the symmetric group, or just general representation theory, that the adjacency matrix of this graph has integer eigenvalues. And they have a nice combinatorial description, which I won't give here. Okay, now let's go to the next topic, non-crossing partitions. A non-crossing partition of the set bracket n, 1 up to n, is a partition of the set bracket n such that if I and j are in the same block, and k and l are in the same block, and I is less than k is less than j and less than l, then these two blocks are the same. We can't have the blocks cross. It's like we have an edge from I to j and an edge from k to l that are going to cross. Not allowed. NC of n will be the set of non-crossing partitions of n, and they form a poset by the relation of refinement. This is a graded lattice of rank n minus 1. And what does it have to do with the absolute order? For every maximal element, or n cycle W of the absolute order, the interval from the identity to W is isomorphic to NCN, the non-crossing partition lattice. A very simple result. The isomorphism is the simplest you can imagine. You take your permutation, write it into cycles, and let the elements of the cycle be the elements of the block of your partition. These will always be non-crossing partitions. And that's the isomorphism. Now we can label the edges of the non-crossing partition lattice. That means we're labeling the cover relations. So if pi tau is an edge of the Hasse diagram, in other words, tau covers pi, then tau will be obtained from pi by merging two blocks, B and B prime. So let the least element of these two blocks be I. Let's say it belongs to B. Then we'll label the edge or cover relation pi tau. We'll call this label lambda pi tau. The largest element j of B, which is less than every element of B prime. It's non-empty because I is an element of B, which is less than every element of B prime. Here's an example. These are two elements of our non-crossing partition lattice. They have blocks. This first one has blocks 3, 5, 8, 7, 9, and some others. We merge them to get the tau. This block 3, 5, 8, 7, 9. 3 is the least element of the two blocks. 5 is the least element of that block that contains 3. That's less than all of these elements. So the label is 5. Then we can label the maximal chains of our non-crossing partition lattice by an n-1 tuple whose elements are just the labels of the cover relations of the chain. This is the edge labeling of NC4. Of course, you don't have time to check everything, but like this 2 I merged 1, 2 with 3, 4. 1 is the least element, 2 is the least element that's less than all the elements of the block 3, 4, so the label is 2. Next, parking functions. A parking function of length n is a sequence of n positive integers whose weakly increasing rearrangement, b1, b2 up to bn, satisfies bi less than or equal to I. Pn will be the set of parking functions of length n. Well, if you're not familiar with parking functions, they have many remarkable properties. The first being that the number of them is n plus 1 to the n minus 1. Not really relevant here. And what is the connection with the non-crossing partition lattice? This is a result I proved in 1997. If you look at the labels of the maximal chains of the non-crossing partition lattice, they're exactly the set of parking functions of length n minus 1. And a priori, the maximal chain labels don't have to be unique. They just form a multi-set, but here they actually form a set. All the parking functions of length n minus 1. So the number of maximal chains is n plus 1 to the n minus 1. It's a result of Cover-Ross. This is illustrated for n equals 3. This is the non-crossing partition lattice for n equals 3. All the partitions of 1 up to 3 are non-crossing. And the labels you see are 1, 2, 1, 1, and 2, 1. These are the parking functions of length 3. Okay, now we are interested in certain enumerative properties of the non-crossing partition lattice having to do with counting certain chains. So if P is a finite graded poset of rank n with a bottom element 0 hat and top element 1 hat, we'll let rho be the rank function of P. So the rank of the 0 is 0 and the rank of 1 is n. For any subset of bracket n minus 1 with r elements, the flag f vector is a function alpha to P. So it depends on P. It takes all the all the subsets of 1 up to n minus 1. It takes such a subset into an integer, namely alpha P of S is the number of chains from 0 to 1, such that if you ignore the 0 and 1 top and bottom elements of the chain, the ranks of these other elements, T1 up to TR, is exactly the set S. So we're counting the chains in P with specified ranks, whose elements have specified ranks, namely the elements of S. So for instance, if S is 1 up to n minus 1, everything, we're counting maximal chains. If S just has one element K, we're counting the number of elements of rank K. The flag H vector, beta P, is also a function from subsets of n minus 1, bracket n minus 1 to z. And this defined as a certain linear combination of the values of the flag F vector. Equivalently, this is saying that alpha P of S is the sum over all subsets T of S, beta P of T. So for a general P, beta P of T does not have any real combinatorial significance. And it could be negative in general. It can be interpreted as an Euler characteristic, but not as a nice combinatorial object number or counting some combinatorial objects. But for certain posets, there is a nice combinatorial interpretation of beta P. So let's define the weak descent set, W dash sigma, of a sequence of integers, A1 up to AN, to be the set of all AI such that AI is greater than or equal to AI plus 1. I call it weak because I allow equality here. So if lambda is any labeling of the edges of the Hasse diagram of a graded poset of rank n with 0 and 1, we'll say it's an R prime labeling if there's a unique, strictly decreasing saturated chain in every interval of P. The labeling of lambda, restricts to the edges of the poset of the interval ST, and we'll define an R prime labeling if these labeling of the saturated chains has a uniquely decreasing saturated chain. So this is a little variation of the definition of an R labeling, where you look at strictly increasing rather than weakly increasing rather than strictly decreasing. It's an irrelevant. It's really an irrelevant change, but it's what is needed here. So an easy fact is that the edge labeling lambda of the non-crossing partition lattice NCN is an R prime labeling, and using basic properties of these labelings, one can show that alpha P of S is a number of non-crossing parking functions of length n minus 2 whose weak descent set is contained in S. Of course, the parking functions are the labels of the maximal chains. So the number of maximal chain labels whose weak descent set is contained in S. Beta P of S will be the number of parking functions of length n minus 2 whose weak descent set equals S. So this is a combinatorial interpretation of beta P of S. In particular, it's non-negative. Here as an example, this is the non-crossing partition lattice NC4. Let's compute beta. It's of 1, 2. So it's alpha of 1, 2, the number of maximal chains, which is 16, then minus alpha of 1, the number of elements of rank 1, which is 6, minus alpha of 2, 6, plus alpha of the chain that consists of just 0 and 1, which is 1. So we get 5. In general, for the NCN, we're going to get the nth Catalan number for beta of bracket n minus 1. And indeed, the non-crossing the parking functions of length 3 with weak descent set 1, 2, there are 5 of them. The weakly decreasing non-crossing parking functions of length 3. Now we want to put the values of the flag H vector beta into a generating function, which is called the Ehrenborg quasi-symmetric function of P for any finite graded poset P of rank n with 0 and 1. So you see it's the sum over all S, subset bracket n minus 1, beta P of S, and this function that's indexing the beta P of S is the L of S, the fundamental quasi-symmetric function indexed by S and N. I'm just assuming that N is fixed in this notation. So you don't have to know what quasi-symmetric functions are, because in the situation I'm looking at, EP will be a symmetric function. So what is the Ehrenborg symmetric function of NCN? Now this, for the non-crossing partition lattice, the quasi-symmetric function will be a symmetric function. So P will be a finite graded poset with 0 and 1 of rank n as usual. And a fairly simple theorem is that for such a poset, if every interval is rank symmetric, has the same number of elements of rank I from S, that's going down from T, then EP is a symmetric function. Now every interval of NCN is self-dual, so it's certainly going to be rank symmetric. So we conclude from this theorem that the Ehrenborg quasi-symmetric function of NCN is a symmetric function. And there's a nice way to compute it combinatorially, which implies that it's E positive. I'll illustrate it with some small examples. Sm is a set of permutations of a multiset M. Now, it's well known, well, it follows from the definition I gave of a parking function, that the parking functions of length n are going to be unions of sets of all permutations of some multisets. Because every permutation of the elements of a parking function is still a parking function. So the parking functions of length 2 are the permutations of the multiset 1, 1 and 1, 2. 3 of them. Well, once we have this decomposition, or equivalently, once we have figured out the weakly increasing parking functions, or weakly decreasing, just picking some canonical element of the multiset, of the permutations of the multiset, then each such multiset is going to give one elementary symmetric function E lambda, and lambda will be given by the part multiplicities of the elements of the multiset. So like this says part multiplicities 2 and 1, so it's going to contribute E2, E1 to the Ehrenborg symmetric function. So we just read off from this collection of multisets that E of NC4 is E1Q plus 3 E2 E1 plus E3. This works for any n, so we see that E of NCN is E positive, and we have a simple combinatorial interpretation of the coefficients. So remember, this information here, this is encoding, this is a generating function for the flag H vector, or equivalently the flag F vector. So a lot of combinatorics is built into this generating function, very simple generating function. Okay, now just sort of as an aside, gamma positivity enters the picture here. Polynomial with real coefficients of degree n is gamma positive if it can be written as a linear combination of polynomials q to the I, 1 plus q to the n minus 2i, this should be q to the 2i. No, this is correct. Yeah, q to the I, 1 plus q to the n minus 2i, so that the coefficients gamma I are non-negative. Now, you can read off immediately from this decomposition that a gamma positive polynomial is palindromic. The coefficients read the same backwards as forwards, and unimodal. In fact, if we have any palindromic polynomial of degree n, it can be uniquely written in this form. So the crux of the definition of gamma positive are the coefficients are non-negative. Okay, so we have a little theorem. If we have any graded poset of rank n with 0 and 1, and if EP, the Ehrenborg quasi-symmetric function, is an E positive symmetric function, then the rank generating function is gamma positive. Well, here's my only proof of my talk, because it's so simple. It's an E positive symmetric function. Now, the E of P is E positive symmetric function. The rank generating function, well, being E positive is going to automatically make it rank symmetric. So we can write the rank generating function in this form. And gamma I just turns out to be the coefficient of E2, E1 to the n minus 2i in capital E of P. So that's positive because we're assuming EP is E positive. So that's the proof. Now, F and C of n was the Ehrenborg quasi-symmetric function of NC of n was E positive. So, as a special case of this theorem, the rank generating function is gamma positive. In fact, this is already well known. The number of elements of rank I is this Narayana number, this explicit number, and it's well known that easy to check that the Narayana numbers are gamma positive. Okay, well, a lot of background information concerning the absolute order and non-crossing partitions I just gave. We can quickly review. I defined the absolute order on Sn. We saw the rank generating function had a nice product formula. The Hasse diagram was a Cayley graph of the symmetric groups, which implied it was vertex transitive, and that the adjacency matrix had integer eigenvalues. All the maximal intervals were isomorphic to NC of n. We had a nice edge labeling of the edges of the Hasse diagram of NC of n. In fact, the labels, which meant that the labels of the maximal chains were just the parking functions. That implied that the labeling was an R prime labeling, which let us set up a nice connection between the ascent sets of the maximal chain labels and the flag H vector of the poset NCN. We defined a generating function for the flag H vector, the Ehrenborg quasi-symmetric function, which was an E positive symmetric function, and that implied the rank generating function was gamma positive. Okay, now I'm going to generalize the absolute order, and that'll imply automatically a generalization of NCN. And we want to see how all of these things generalize, or to what extent they do. A lot of stuff to think about. Here's a generalization. We fix n. We'll let mu be a partition with n minus 2 terms. So a weakly decreasing sequence of non-negative integers, and we'll put in the extra condition that mu I is less than or equal to n minus I minus 1. That is saying our partition is contained in the staircase shape, n minus 2, n minus 3, down to 1. Not really relevant, but the number of such mu's is a Catalan number Cn minus 1. I could say all my definitions I'm going to give could be done for mu being a larger staircase, beginning with n minus 1 instead of n minus 2. But if the staircase is not contained in this smaller one, but in the larger one, then all my definitions are, you might say, everything is going to reduce to smaller cases. Yeah, and I won't give anything new by enlarging the staircase, and it's much simpler to deal with these smaller staircases and not to have to worry about reducing to smaller cases. Okay, so S, fraktur S bracket mu, will be the set of all partitions in Sn satisfying Wi is less than or equal to n minus mu I. For example, if mu is empty, then the condition is wi is less than or equal to n. That's automatically true anyway, so we get the full symmetric group. If mu is just the partition 1, then the condition becomes all w in Sn such that w1 not equal to n. The number of such partitions is all partitions n factorial minus the number of ones for which w1 is n, which is n minus 1 factorial. That has a nice product formula for that number. Another way of thinking of this subset of Sn, S bracket mu, is looking at all permutations in Sn whose permutation matrix avoids the reflected shape mu in the upper right-hand corner of an n by n square grid. So here's an example. What I mean by this: n equals 8 by 8 grid. Mu will be 4, 2, 2, 1, so we sort of black out the partition, fair shape 4, 2, 2, 1 from the upper right-hand corner. Then we look at a permutation matrix that avoid, so that the ones avoid this shape mu. All these blank white, all the blank squares are zeros in our permutation matrix. This is the matrix of the permutation 3, 5, 2, 1, 7, 6, 1, 8, 4. This 3, means the 1 is in the third column here, etc. So these are the permutations that are contained in S bracket mu. Absolute order of Sn bracket mu is just the absolute order of Sn restricted to S bracket mu. Here's an example. N equals 4, mu equals 1, 1. So the permutations we're looking at satisfy W1 not equals 4, W2 not equals to 4. This is what the absolute order looks like, restricted to those permutations. There's happens to be 12 of them. There's some simple properties of this poset. It's graded of rank n minus 1 and it inherits the rank function from the absolute order. So we're counting, we're counting by number of cycles, or really the rank is n minus the number of cycles. 4 cycles, 3 cycles, 2 cycles, and 1 cycle at the top. Since it's graded of rank n, these single cycles will be the maximal elements. The Hasse diagram, considered as a graph, is a regular bipartite graph, and the degree is the number of transpositions in S bracket mu, which you can easily see is n choose 2 minus the sum of the parts of mu. It's also easy to see that the rank generating function for this poset has a nice product formula, just like it did for the absolute order. Since the poset is graded of rank n minus 1, the number of maximal elements will just be the leading coefficient of this rank generating function. So we have a nice product formula for the number of maximal elements. Remember, for the absolute order itself, with the number of cycles, n minus 1 factorial. Now what about vertex transitivity of the Hasse diagram of S bracket mu? For the absolute order itself, the Hasse diagram was a Cayley graph, so we automatically got vertex transitivity. But in that, also, since the generators were conjugacy class, we got integer eigenvalues. Well, it's a much more complicated situation for general mu. We don't know when the Hasse diagram is vertex transitive, but it often is. It is, first of all, it is for n less than or equal to 4. For n equals 5, there's 14 values of mu altogether, and only one of them, mu equals 2, 1, do we not get vertex transitivity. We get two orbits of sizes 18 and 36. For n equals 6, there's 42 mu's altogether. 9 of them are not vertex transitive. With Sejong Bang, we proved that if mu is a single row, k, so a single part equal to k, then we do get vertex transitivity. Okay. What about the eigenvalues? We always had integer eigenvalues for the absolute order. Well, Phil Hanlon proved a theorem in 1996. It's in a very different context, but his theorem is equivalent to saying that the eigenvalues of the Hasse diagram always are integers, and they have combinatorial descriptions. I won't give them here. It's a little complicated. I should say that Hanlon develops his work in terms of not the absolute order, but in terms of rook theory. Remember, S bracket mu was could be considered as a set of permutation matrix whose ones fell off of the set of squares mu. Well, here the ones we consider as rooks being placed on a Ferrer's diagram. So that suggests developing a general theory of random walks on the Hasse diagram. And in particular, what is the mixing time? Standard question you can ask about random walks on graphs. Here is an example. The example I gave before of these 8 ones in a permutation matrix. We can regard the ones as rooks in the Hasse diagram consisting of the white squares, well, where you reflect 180 degrees. So we have the shape is 8, 8, 8, 8, 7, 6, 6, 4. So all of this stuff that I'm doing regarding Sn bracket S bracket mu can be regarded as part of rook theory also. Okay, now we come to the non-crossing partition lattice, NCN. Remember, for the absolute order, any maximal interval from the identity to a cycle is isomorphic to NCN. So we can look at the maximal elements of the absolute order, bracket mu, and ask what are the maximal, there will be some generalization of NCN. Well, we don't know for two maximal elements of abs Sn bracket mu whether they're exactly what properties they have in common, like whether they're even isomorphic, the strongest possible property, as for the regular absolute order. They're always graded of rank n minus 1. But we don't even know if they have the same number of elements. Maybe this is not so hard to prove. Or more generally, the same rank generating function, even more generally, the same flag f vector, or the ultimate generalization, whether they're isomorphic. But there is a canonical maximal element, which is the only one I'm going to consider here. Because mu is contained in this particular staircase, we always have that the cycle 1, 2, up to n is in the absolute order, bracket mu. So we'll define NCN bracket mu to be the interval from the identity to the cycle 1, 2, up to n. The canonical mu generalization of NCN. So I don't know what happens for the other maximal elements here. Like whether we're even going to get isomorphic or even posets with the same number of elements. But I suspect that that does happen. Now every edge of the Hasse diagram of this poset NCN bracket mu is also an edge of the Hasse diagram of NCN. So we can just use the same edge label that we did before for NCN. And so we get a edge labeling of NCN bracket mu just by restriction. So the maximal chain labels of NCN bracket mu are parking functions because that's was the same for NCN, and the maximal chain labels are distinct because that was true for NCN. Now what are these maximal chain labels? Well, a crucial lemma is that if we have a maximal chain label A1 up to AN minus 1 of NCN bracket mu, then we can transpose two adjacent terms and it will still be a maximal chain labeling. This is a straightforward analysis, but there's many cases to consider here, but very elementary proof. Proves this lemma. What does that mean? Every permutation of this multiset, A1 up to AN minus 1, every permutation is a maximal chain label because it can be generated by adjacent transpositions. So the set of weakly increasing parking functions of length, there is a set of weakly increasing parking functions of length n minus 1 such that the set of maximal chain labels of NCN bracket mu is just given by all the permutations of the multiset M mu, whose elements are the elements of the weakly increasing parking functions that are labels of NCN bracket mu. In other words, the set of all maximal chain labels is a set of permutations of multisets mu, and that multiset consists of the elements of certain weakly increasing parking functions. And as a corollary, since we know the edge labeling is exactly, we can conclude the edge labeling lambda of NCN mu bracket mu is an R prime labeling. This is automatically going to give to us that the Ehrenborg quasi-symmetric function is E positive, but it also implies, for those who know what this means, that these posets NCN bracket mu, by the way, this sub n, I've also been denoting parentheses n. Yeah. The notation hasn't been completely consistent, but this corollary implies that this is a Cohen-Macaulay poset. Well, here's an example that maybe will make things a little more clear. This is n equals 4, mu equals 1, 1. In other words, W1, we're looking at permutations that W1 does not equal 4 and W2 does not equal 4. Earlier I showed the whole absolute order bracket mu of this poset, and here is the interval from the identity to the canonical cycle. 1 goes into 2, goes into 3, goes into 4, goes into 1. You can check using the labeling rule I defined before. These green numbers are the edge labels, and the multiset, well, the set of edge labels are these. There's 9 of them. These are just the permutations of 1, 2, 3 and 1, 1, 3. So you look at the part multiplicities of these multisets. There's one with 3 parts equal to 1, 3 part multiplicities equal to 1, and one where the part multiplicities are 2 and 1. So this is the Ehrenborg quasi-symmetric function, well actually symmetric function of this poset. It tells you the complete flag F vector. But one question remains. Excuse me? One question remains. How do you find these coefficients of these E lambdas without going through this laborious process, labeling all the chains and seeing what you get? Well, first I should mention that since the Ehrenborg quasi-symmetric function, or symmetric function, is E positive, remember I explained earlier why that implies the rank generating function is gamma positive. So for all of these posets, NCN bracket mu, the rank generating function will be gamma positive. So now let's come to the question of the coefficients of the E lambdas. I'm going to define a graph associated with this data n and mu. So we'll think of mu as a Young diagram in the upper right hand corner of the square grid n cross n. Gamma n mu will be the graph on the vertex set 1 up to n, whose edges ij, where I is less than j, are those ij where I is less than j and ij is not contained in mu. Here's an example. If n is 5 and mu is 2, 1, so I blacked out 2, 1, I look at all squares above the main diagonal. That'll be, I'm looking at the matrix coordinates here. Above the main diagonal will mean that I is less than j, and I have to avoid 2, 1. So we're going to get a graph on the vertices 1 up to 5 with edges 1, 2, 1, 3, 2, 3, 2, 4, etc. That is this graph down here. So that is the graph gamma n mu. This, as an aside, these graphs gamma n mu are exactly the canonically labeled, that is, they're labeled from 1 to 5 in this sort of canonical way, canonically labeled unit interval graphs, the graphs for which ICECA proved to have E-positive chromatic symmetric functions. But this is just a side remark because I don't know any connection between chromatic symmetric functions in this talk. Maybe somebody can figure something out. That would be very interesting. Okay, so here's a big theorem. The coefficient of E lambda in the Ehrenborg quasi-symmetric function of NC and bracket mu is a number of non-crossing partitions rho of bracket n minus 1 of type lambda, that is the block sizes or the parts of lambda, lambda 1, lambda 2, etc., such that if A is in the same block of rho and A is less than B, then A, B minus 1 is an edge of the graph. So, well, if you haven't absorbed this definition, at least you can appreciate it's a very simple combinatorial definition. But here is an example from my previous slide. This graph. N is 5, mu is 2, 1. The non-crossing partitions that arise here are these 4. For instance, 2, 3, 1, 4 appears because 2, 3 is, well, 2 and 3 are in the same block. 2 is less than 3, so the condition says that 2, 4 should be an edge of the graph. Indeed it is. Note that the non-crossing partitions are on the set bracket n minus 1. The graph has n vertices. So 3, 4, 1, 2 being a block, being a valid non-crossing partition would say that 3, 5 is an edge. Yeah, you have to use this extra vertex in the definition. So that's the theorem. We look at these non-crossing partitions. We look at the block sizes. One with 4 one-element blocks gives us an E1 to the 4th. 3 with the blocks of sizes 2, 1, 1, so that gives us 3 E2 E1 squared. So you might say we have this very simple combinatorial rule for determining the flag F vector of the poset, ENCN bracket mu. That means like all this maximal chains, its rank generating function, and all this intermediate information. Now, the rank generating function is built into the, this Ehrenborg symmetric function. And remember, it's gamma positive. So we should have a nice rule for the gamma i's. And indeed, it's exactly the same type of theorem here, except rather than looking at non-crossing partitions, we look at non-crossing matchings. Gamma I is a number of non-crossing matchings with I edges, so it'll have n minus 2i singleton vertices with the exact same condition. If A and B are in the same block of row, meaning if they form an edge, then AB plus 1 must be an edge of gamma n mu of our graph. Then the rank generating function is given by this gamma decomposition here. So a very simple, explicit combinatorial definition of the gamma i's. Now here, the valid non-crossing matchings also are the non-crossing partitions. We didn't have a block of size 3 or more in this example, but the fact that we have this one with 4 singletons gives us a 1 plus q to the 4th, and this one with 2 singletons, 3 of them with 2 singletons gives us 3q, 1 plus q squared. So the rank generating function is this. And a side remark, does this rank generating function always have real zeros? It's true for n less than or equal to 6, and it's known in some certain special cases for all n. Now, I want to conclude with there's some other object, completely different object, that actually gives a completely different viewpoint on what I've been doing. Non-crossing bond lattices. Q will be any simple graph on the vertex set bracket n. Simple means no multiple edges, no loops from a vertex to itself. A connected partition of G is a partition such that the restriction to every block is connected. The induced subposet on any block is a connected subgraph. The bond lattice is a set of connected partitions ordered by refinement. Probably most of you are familiar with this. It's a geometric lattice. It's an intersection lattice of a hyperplane arrangement and has a lot of amazing properties. Its characteristic polynomial is a chromatic polynomial of the graph. But here we're going to only look at non-crossing bonds. That is, not every partition that's connected, but the ones whose only those connected partitions that are non-crossing. This is the non-crossing bond lattice. We can define it for any graph whose vertices are, well, the vertices have to be linearly ordered to define non-crossing. So we make it on the vertex set bracket n. Here's an example. When mu is 1, the partition 1, and n is 4, this graph turns out to be isomorphic to the complete graph K4 minus an edge. This is what its complete bond lattice looks like. Only one of these partitions is crossing. 1, 3, 2, 4. If we remove it, we're going to actually get our non-crossing partition graph NC4 bracket this partition 1. And that's a general theorem, another description of NCN bracket mu, the non-crossing bond lattice of gamma n mu. So remember, these gamma n mu's are the unit interval graphs. So non-crossing bond lattices of unit interval graphs are very interesting creatures. For arbitrary graphs, they don't seem so interesting. But maybe there's other classes of graphs for which they are interesting. It's something else to look at. Okay, so I covered a whole lot of stuff here and left you with a few nice problems to think about. So thank you for listening.